There's a place in the universe you can never reach. Not because it's too far away, not because you lack the technology, but because the space between you and it is expanding faster than light itself can travel. Right now, at this very moment, galaxies are crossing an invisible threshold. Once they pass it, no signal they send, no light, no information, no evidence of their existence will ever reach us again. They vanish, not into darkness, but into something far stranger, a region of space-time that is, for all practical purposes, disconnected from our reality. We call this boundary the cosmic event horizon, and it's not some distant theoretical concern. It's happening now. Thousands of galaxies disappearing every day, slipping beyond the edge of the observable universe like ships sailing off an ancient map marked "Here be dragons." What if I told you that the universe has an edge, not in space, but in time? Not a wall, but a horizon beyond which the laws of physics themselves might cease to have meaning. Today, we journey through evidence that challenges everything we think we know about the cosmos. We'll explore what happens at the boundary of existence itself. We'll discover why some of the universe is already forever lost to us, and we'll confront a possibility so profound it reshapes our understanding of reality. Subscribe to my channel, Relativity Vault. Also, tell me in the comments, which country are you watching this video from, and what time is it there right now? Prepare yourselves. We begin. In 1929, astronomer Hubble made an observation that would shake the foundations of cosmology. Analyzing light from distant galaxies through the 100-inch telescope at Mount Wilson Observatory, he discovered something extraordinary. Nearly every galaxy in the universe was moving away from us. But here's what made it truly remarkable. The farther away a galaxy was, the faster it was receding. A galaxy twice as distant wasn't just moving away twice as fast. The relationship was perfect, mathematical, precise. This wasn't random cosmic motion. This was something fundamental about the universe itself. The universe, Hubble realized, was expanding. Not expanding into anything, but expanding in on itself. Space itself was growing, stretching, pulling galaxies apart like dots on an inflating balloon. Think about that for a moment. Every cubic meter of space, every point between galaxies is expanding. Between your eyes and this screen, space is expanding. The effect is negligible at small scales. Molecular forces and gravity easily overcome it. But across cosmic distances, across millions and billions of light years, the expansion becomes the dominant force in the universe. Now, Einstein had already established something crucial. Nothing can move through space faster than light. This wasn't just a speed limit for spaceships, it's a fundamental constraint on causality itself. Information, cause and effect, reality as we understand it, all bound by the speed of light. But here's where it gets strange. Einstein's equations say nothing can move through space faster than light, but they place no limit on how fast space itself can expand. Space isn't moving through anything. It's the fabric itself that's growing. Picture two galaxies, each stationary in their local patch of space. Neither is moving, yet the space between them is expanding so rapidly that they're separating faster than light could travel between them. They're not violating relativity, they're revealing something deeper about the nature of space-time itself. The expanding horizon. In the decades following Hubble's discovery, cosmologists began calculating the implications. If space is expanding and the expansion rate is measurable, then there must be a distance beyond which galaxies are receding faster than light. They called it the Hubble sphere, and it exists approximately 14.5 billion light-years away from us in every direction. Beyond this boundary, space is expanding so rapidly that light from those regions can never reach us. Not eventually, not given infinite time, never. The expansion will always outpace the light's journey towards us. But the universe didn't stop at revealing this static boundary. In 1998, two teams of astronomers studying distant supernovae made a discovery that would earn them the Nobel Prize and fundamentally transform our understanding of cosmic expansion. The universe wasn't just expanding, the expansion was accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees had found evidence of what cosmologists now call dark energy, a mysterious force that pervades all of space, pushing against gravity, driving galaxies apart at an ever-increasing rate. The acceleration changed everything. With the expansion speeding up, the cosmic event horizon was no longer static, it was shrinking. Let me explain what this means. Right now, the observable universe extends roughly 46.5 billion light-years in every direction. That's larger than 14 billion light-years because space has been expanding while ancient light traveled toward us. But the cosmic event horizon, the boundary beyond which we can never receive signals, sits at about 16 billion light-years away. Here's the crucial part. As the universe continues to accelerate, this horizon is moving inward. Galaxies that are currently within our observable universe, galaxies we can see right now, are approaching this boundary, and once they cross it, they're gone forever. Not hidden, not obscured, but fundamentally disconnected from our causal universe. They might as well exist in another dimension, another reality entirely. The mathematics is unambiguous. In a universe dominated by accelerating expansion, we're living inside a shrinking sphere of causality. Each moment, more of the universe slips beyond our reach. But this represents just one piece of a much larger puzzle hidden in the very structure of space-time itself. Using data from the Hubble Space Telescope and the Sloan Digital Survey, cosmologists have mapped the expansion of the universe in unprecedented detail. What they've discovered is sobering. Currently, approximately 150 million galaxies lie within our observable universe. But every day, roughly 20,000 galaxies cross the cosmic event horizon. Not disappearing from view, that will take billions of years as their light continues reaching us, but crossing the point of no return where their future light can never reach us. Think about what this means. Right now, at this moment, there are galaxies experiencing their final moments of causal contact with our universe. The light they emit today will eventually reach us, growing increasingly redshifted, stretched to longer wavelengths by the expansion of space it travels through. But there will come a final photon, the last bit of information that can ever traverse the gap between us. After that, nothing, ever. Astronomers at the European Southern Observatory have calculated the rate at which this is occurring. In the next trillion years, 97% of the galaxies currently observable will have crossed beyond the cosmic horizon. The universe we can interact with, the universe that can interact with us, will shrink to just our local group of gravitationally bound galaxies. But the evidence becomes even stranger when we examine what happens to light as it approaches this boundary. Light from distant galaxies is redshifted, stretched to longer wavelengths by the expansion of space. The effect is proportional to distance. A galaxy at 1 billion light-years shows a small redshift. A galaxy at 10 billion light-years shows a dramatic redshift, its ultraviolet light stretched into the infrared. But there exists a region cosmologists call the redshift desert, a zone where galaxies should exist, but where we find almost nothing. Not because they're not there, but because their light has been stretched beyond what any telescope can detect. The James Webb Space Telescope, launched in 2021, has pushed into this desert further than ever before, detecting galaxies at redshift Z equals 13, existing just 300 million years after the Big Bang. But even JWST encounters a limit. Beyond a certain distance, the expansion so thoroughly redshifts light that no telescope, regardless of sensitivity, can capture it. We're not limited by technology, we're limited by the structure of space-time itself. The cosmic microwave background, the afterglow of the Big Bang, represents the oldest light in the universe. It's been traveling through space for 13.8 billion years, originating from a time when the universe was just 330,000 years old. This light has been redshifted by a factor of 1100. Photons that were emitted as visible light now arrive as microwave radiation, their wavelengths stretched by the expansion of space. But here's what's remarkable. The CMB represents a natural horizon. The matter that emitted this radiation is now roughly 46 billion light-years away, well beyond our causal horizon. We're seeing the light it emitted long ago, but the actual atoms that produced it are now forever beyond our reach. In 2013, the Planck satellite mapped the CMB with unprecedented precision, revealing temperature fluctuations of just 1 part in 100,000. These tiny variations represent the seeds of all cosmic structure, the quantum fluctuations that would eventually grow into galaxies and galaxy clusters. But embedded in these fluctuations, researchers at Princeton University discovered something unexpected: anomalies that shouldn't exist, large-scale patterns that seem to violate the assumption of cosmic isotropy, the idea that the universe should look the same in all directions. One anomaly, dubbed the cold spot, spans 1.8 billion light-years and shows a temperature 70 microkelvins colder than its surroundings. Various explanations have been proposed: a supervoid draining energy from passing photons, quantum fluctuations amplified to cosmic scales, or even a signature of a collision with another universe. But some cosmologists suggest something more disturbing. We might be seeing evidence of structure beyond our cosmic horizon, massive gravitational features whose effects leak across the boundary through mechanisms we don't yet understand. The implications are staggering. If information can cross the horizon, even subtly, then the boundary might not be as absolute as our equations suggest. Black holes taught us something profound about event horizons. When matter falls past a black hole's event horizon, information appears to be destroyed, violating a fundamental principle of quantum mechanics. This is the black hole information paradox, and it's driven theoretical physics for decades. Stephen Hawking's work on Hawking radiation suggested that black holes eventually evaporate, returning information to the universe through subtle quantum correlations. The event horizon, in this view, isn't a true barrier to information, just a one-way membrane that processes and scrambles information before releasing it. But what about the cosmic event horizon? Research published in Physical Review D by cosmologists Sean Carroll and his colleagues at Caltech explores an unsettling possibility: The cosmic event horizon might face a similar paradox. Galaxies crossing this boundary don't just become invisible, they might experience something far stranger from their perspective. From our viewpoint, light from these galaxies becomes increasingly redshifted, time appearing to slow down asymptotically as they approach the horizon. But from the galaxy's perspective, time continues normally. They simply cross the boundary and continue existing in a region of space-time forever disconnected from ours. Who's right? Both perspectives are valid within their own reference frames. This creates a kind of cosmic complementarity, different observers experiencing fundamentally different realities. The question becomes, does information about those galaxies persist in our universe, encoded somehow at the boundary, or is it truly lost? And if it's lost, does that violate the same quantum principles challenged by black holes? The answer might lie in one of physics's most profound insights, the holographic principle. Developed by Gerard 't Hooft and Leonard Susskind in the 1990s, the holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that region. Like a hologram encoding three-dimensional information on a two-dimensional surface, the universe might encode all information about its interior on its cosmic horizon. If this is true, then nothing is truly lost when galaxies cross the event horizon. The information is preserved, encoded in subtle quantum correlations at the boundary itself. From our perspective, the galaxy disappears, but its informational content persists, imprinted on the structure of space-time at the cosmic edge. Juan Maldacena's ADS-CFT correspondence, a mathematical duality between gravity in a space and quantum field theory on its boundary, provides mathematical support for this idea. If the universe operates according to holographic principles, then the cosmic horizon isn't a boundary at all. It's a translation surface where physics in one description becomes physics in another. Research teams at the University of Cambridge are exploring how this might manifest observationally. Could we detect subtle correlations in the cosmic microwave background that represent information encoded holographically? Could quantum entanglement extend across the horizon, creating connections between our observable universe and the realm beyond? But the most remarkable discovery involves the connection between cosmic horizons and the multiverse. In eternal inflation theory, developed by Alan Guth, André Linde, and others, the universe we observe is just one bubble in an infinitely expanding foam of space-time. Each bubble has its own cosmic horizon, its own observable region, potentially its own physical laws. The boundaries between these bubbles are cosmic horizons. Cross one, and you're not just entering empty space, you're potentially entering a region where physics operates differently, where the speed of light might vary, where the strength of gravity could differ, where even the number of spatial dimensions might be different. Evidence for this comes from those anomalies in the cosmic microwave background. If our bubble universe collided with another in the early cosmos, we'd expect to see exactly what we observed: large-scale patterns breaking cosmic symmetry, cold spots, aligned structures that shouldn't exist in a purely isotropic universe. Research published in 2015 by cosmologists at University College London identified 4 anomalous regions in the CMB that could represent collision signatures. The statistical likelihood of these patterns arising by chance is less than 1 in 10,000. We might be living inside a universe with visible scars from collisions with other universes. regions where cosmic horizons touched and information leaked across. The evidence extends beyond the cosmic microwave background into the realm of quantum mechanics itself. To understand what's really happening at the cosmic horizon, we need to examine the mathematics that describes expanding space. The Friedmann equations, derived from Einstein's general relativity, govern how the universe expands. They relate the expansion rate, the Hubble parameter, to the energy content of the universe: matter, radiation, and dark energy. Currently, dark energy comprises roughly 68% of the universe's total energy budget. This dark energy behaves like a cosmological constant, an inherent energy density of empty space itself. And crucially, its density doesn't dilute as space expands. As the universe grows, dark energy becomes increasingly dominant, driving ever faster acceleration. The cosmic event horizon's distance can be calculated from these equations. It's located where the expansion velocity equals the speed of light, b equals c over h, where c is light speed and h is the Hubble parameter. Currently, that places the horizon at approximately 16 billion light-years. But here's what forces us to reconsider fundamental assumptions about causality. As dark energy dominates, this horizon shrinks. Eventually, in the far future, it will contract to encompass only our local group of gravitationally bound galaxies. Physicist Lawrence Krauss at Arizona State University describes this as cosmic censorship, the universe hiding most of itself from observation, not through any conspiracy, but through the simple geometry of accelerating space-time. Not all physicists agree on what happens at the cosmic horizon. Several competing interpretations exist, each with profound implications. The first interpretation is straightforward. The horizon represents a true causal boundary. Information cannot cross it in either direction. Galaxies beyond it exist in a region of spacetime permanently disconnected from ours. This is the standard view among most cosmologists. The second interpretation, supported by some quantum gravity theorists, suggests the boundary is permeable to quantum information. Just as black holes might preserve information through Hawking radiation, cosmic horizons might allow information to leak across through quantum mechanical processes we don't yet understand. Roger Penrose at Oxford University has proposed a third possibility. The cosmic horizon might not persist indefinitely. If dark energy isn't truly constant, if it evolves over cosmic timescales, the horizon could expand again in the distant future, potentially allowing causal contact to be re-established. A fourth interpretation comes from eternal inflation theory. Our cosmic horizon is just one boundary in an infinite hierarchy. Beyond it lie other bubbles, other horizons, potentially an infinite fractal structure of nested, causally disconnected regions. Each interpretation leads to different predictions about what future observations might reveal, and each forces us to confront deep questions about the nature of existence itself. What does it mean to exist in a universe where 97% of all galaxies will eventually become forever inaccessible? What does it mean for reality to have edges, boundaries beyond which cause and effect cease to operate? These aren't just abstract philosophical questions, they're challenges to our understanding of what the universe fundamentally is. What technologies might help us probe these mysteries further? The next generation of telescopes is already under construction. The extremely large telescope in Chile, with its 39-meter mirror, will see first light in 2028. The Nancy Grace Roman Space Telescope will launch in 2027, mapping the universe's large-scale structure with unprecedented detail. These instruments will push deeper into the redshift desert, finding galaxies at the very edge of observability. They'll measure the expansion rate with precision enough to determine whether dark energy is truly constant or evolving. They'll search for subtle signatures of information encoded at the cosmic horizon. But there are limits. No telescope, no matter how advanced, can observe beyond the cosmic event horizon. We're constrained not by engineering, but by physics itself. However, theoretical physicists at CERN and Fermilab are exploring whether particle accelerators might reveal clues. If quantum mechanics allows information to leak across cosmic horizons, that leakage might manifest in subtle correlations detectable in high-energy physics experiments. Gravitational wave astronomy offers another avenue. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect gravitational waves from massive cosmic events. These ripples in space-time might carry information that crosses boundaries impermeable to light. Recent breakthroughs suggest where this is all heading. In 1 trillion years, the cosmic horizon will have contracted so severely that only our local group remains observable. The Milky Way, Andromeda, and a few dozen smaller galaxies will merge into a single massive galaxy, an island universe surrounded by expanding emptiness. Astronomers living in that era, if any exist, will look out at a seemingly static universe. They'll have no evidence of cosmic expansion, no red-shifted galaxies, no cosmic microwave background, which will have been stretched to wavelengths longer than the horizon itself. They'll be unable to discover the Big Bang, unable to infer that the universe was ever different, unable to realize that their observable universe is shrinking. This has profound implications for our current understanding. How much of the universe's history are we unable to see because it's already crossed our horizon? What evidence has been lost to us not through time, but through space? In 10 to the 100 years, even the cosmic horizon will have contracted past our local group. Individual stars will cross it, disappearing from the universe. Eventually, if dark energy remains constant, every object not bound together at the smallest scales will be isolated beyond its own horizon. This is the ultimate fate in a universe dominated by accelerating expansion. Cosmic loneliness on an absolute scale. Not just darkness, but true disconnection. Each surviving structure existing in its own isolated pocket of space-time, unable to signal or communicate with anything else. But what happens at the moment of crossing? Does consciousness experience it? If a galaxy crosses the horizon, does it cease to exist from our perspective, or does it persist in some encoded form? These questions blur the line between physics and philosophy. They force us to ask, what does it mean to exist in a relative sense? If an object exists but can never interact with us again, never influence our future, never send information our way, does it still exist in any meaningful sense for us? Some cosmologists suggest we need a new framework entirely, one that treats existence itself as observer-dependent. In this view, the universe doesn't have an objective structure independent of observation. What exists for one observer might not exist for another, and both perspectives are equally valid. This connects to deeper puzzles in quantum mechanics, where measurement and observation play fundamental roles in determining reality. Perhaps the cosmic horizon represents the ultimate observer effect, the universe's way of limiting what any observer can meaningfully call real. The most profound implications emerge when we consider what lies beyond. What exists beyond the cosmic horizon? The standard answer is simple: more universe, more galaxies, more stars, more space-time, all following the same physical laws, but forever disconnected from our causal domain. But this assumes the universe is homogeneous beyond our horizon. What if it's not? Some cosmological models suggest the universe could be highly inhomogeneous at scales larger than our horizon. We might live in an unusually dense region or an unusually empty one. The physics we observe, the constants of nature, the strength of forces might be local properties, not universal ones. If the multiverse interpretation is correct, each horizon-bounded region could have different physics entirely. Cross the boundary, and you're not just entering unreachable space, you're entering a realm where reality operates according to different rules. André Linde's chaotic inflation model suggests exactly this. In eternal inflation, bubble nucleation creates regions with varying properties. Our observable universe is one bubble. Beyond our horizon might lie bubbles where electrons are more massive, where gravity is stronger, where time flows differently. We can never test this directly. The horizon prevents information exchange. But we can look for indirect evidence, those anomalies in the cosmic microwave background, patterns that suggest our bubble collided with another in the early universe. Here's where things get truly strange. If we live in a simulated universe, a hypothesis taken seriously by some physicists and philosophers, the cosmic horizon might represent something entirely different, a computational boundary. Think about it. If you were simulating a universe, you wouldn't simulate regions that can never interact with your observers. You'd only compute the observable universe, letting the rest exist as mathematical abstraction until it becomes relevant. The cosmic horizon in this interpretation represents the edge of active computation. Beyond it lies not more simulated space, but unrendered potential, like the fog of war in a video game, concealing regions not yet needed. This sounds like science fiction, but it connects to real questions in physics. Why does the universe appear fine-tuned for observation? Why do quantum states seem to collapse when measured? Why does the cosmic horizon exist at exactly the distance where space expands faster than light? Philosopher Nick Bostrom's simulation argument suggests we might have up to a 50% chance of living in a simulated reality. If so, every cosmic mystery, including horizons, might have dual interpretations, physical and computational. We can't distinguish between these possibilities. A perfectly simulated universe would be indistinguishable from a real one. The horizon might be a physical boundary imposed by space-time geometry, or it might be an algorithmic limit imposed by finite computational resources. Either way, it represents the edge of what we can ever know. This brings us to the deepest question of all. What does the cosmic horizon tell us about the nature of reality itself? Unless unradically changes, unless dark energy decays, unless we discover physics beyond general relativity, unless the multiverse interpretation allows for horizon crossing, most of the universe will forever remain beyond our reach. This challenges our intuitions about existence. We want to believe in an objective reality, a universe that exists independent of observation. But the cosmic horizon suggests reality might be inherently perspectival. What exists for us, what can causally affect us, might be all that meaningfully exists at all. Physicist John Wheeler proposed that the universe is participatory, that observation and existence are fundamentally intertwined. The cosmic horizon might be the clearest expression of this principle. The universe only exists insofar as it can be observed and interacted with. Beyond the horizon, the question, does it exist, might not have a definite answer. It exists mathematically as a solution to equations, but it doesn't exist causally, can't exist observationally, might not exist meaningfully in any sense we can coherently define. We're forced to confront the possibility that the universe is larger than reality, that there might be regions governed by our physics, described by our mathematics, but forever disconnected from anything we could ever call real. We began this journey with a simple observation. The universe has an edge, not in space, but in causality. Not a wall we might one day cross, but a horizon beyond which interaction itself becomes impossible. We've explored how this horizon arises from the accelerating expansion of space, how galaxies cross it daily, disappearing forever from our causal universe, how the boundary might encode information holographically, preserving what appears lost, how it connects to black holes, quantum mechanics, and the deepest puzzles in physics. We've confronted the implications, a shrinking sphere of observability, a future where our descendants see only a fraction of what we can observe, an ultimate destiny of cosmic isolation. But we've also discovered something profound. The horizon isn't just a limit, it's a window into the nature of reality itself. It reveals that existence might be observer-dependent, that what we call the universe might just be one bubble in an infinite structure, that the boundaries we encounter might tell us more about reality than the regions we can explore. The current scientific consensus is clear. Unless our understanding of dark energy changes dramatically, the cosmic horizon is real and permanent. Most of the universe will become forever inaccessible to us and our descendants. Yet this knowledge doesn't diminish the wonder of existence. If anything, it enhances it. We live in a brief cosmic moment when the universe is maximally observable, when we can still see the afterglow of creation, when evidence of cosmic history hasn't yet slipped beyond the edge. We're fortunate to exist at a time when the universe reveals itself so clearly, when we can map the cosmic web, trace the history of space-time, and understand our place in the vast structure of existence. The universe has an edge. Beyond it lies mystery, perhaps more universe, perhaps other realities, perhaps something we lack the concepts to imagine. We'll never know for certain. The horizon ensures that. But the questions remain, and in asking them, in pushing against the boundaries of knowledge, we participate in the universe's attempt to understand itself. The edge of everything is also the beginning of wonder. Recent developments in quantum information theory have revealed something profound about horizons in general, whether black hole horizons, cosmic horizons, or the event horizons of accelerating observers. All horizons, according to research from the Institute for Advanced Study, share fundamental properties. They represent boundaries in information space, not just physical space. They're places where information density approaches theoretical limits, where entropy of a region equals its boundary area rather than its volume. This is the essence of the holographic principle, and it applies to cosmic horizons just as it applies to black holes. But here's what makes it remarkable. If information is truly encoded holographically at the cosmic horizon, then the horizon isn't a barrier, it's a translation surface. Information that appears to cross into unreachable space doesn't disappear, it gets encoded in the quantum structure of the boundary itself. Mathematician Edward Witten's work on ADS/CFT correspondence provides a mathematical framework for this. Though ADS, anti-de Sitter space, doesn't match our universe's geometry exactly, the principles might generalize. The physics inside a volume might be completely described by quantum field theory on its boundary. If this applies to our universe, then everything beyond the cosmic horizon, all those galaxies, all that space, all those potential civilizations might be encoded in the quantum structure of the horizon itself, not lost, but transformed into another description of the same physical reality. Teams at the Max Planck Institute for Gravitational Physics are exploring whether we can detect this encoding. If the holographic principle holds for cosmic horizons, there should be subtle correlations in the cosmic microwave background, patterns too specific to arise by chance, signatures of information compressed onto the boundary of our causal domain. Quantum mechanics allows for impossibilities. Particles can tunnel through barriers they shouldn't be able to cross. Virtual particles pop in and out of existence. Entanglement creates correlations that seem to violate locality. Could quantum mechanics allow information to tunnel across the cosmic horizon? Theoretical work by cosmologist Raphael Bosso at UC Berkeley suggests it might. Just as Hawking radiation allows information to escape black holes through quantum tunneling, there might be mechanisms allowing information to cross cosmic horizons. The process would be subtle, not a direct transmission of signals. That would violate relativity, but quantum correlations established before the horizon formed might persist across it. Entangled pairs of particles, one on each side of the boundary, could maintain their correlation even after causal contact is severed. This creates a loophole in the horizon's absoluteness. While no classical information can cross, quantum information, encoded in entanglement, in subtle correlations, in the holographic structure itself, might leak through. Evidence for this could show up in several ways. Astronomers at Caltech are searching for subtle anomalies in galaxy distributions near the horizon, patterns that might indicate quantum information exchange. High-energy physicists are looking for signatures in cosmic ray data that might represent quantum tunneling from beyond the cosmic boundary. So far, nothing definitive has been found, but the search continues, driven by a tantalizing possibility. The horizon might be permeable in ways we don't yet understand. Stephen Hawking's chronology protection conjecture states that the laws of physics prevent time travel, protecting causality from paradoxes. But cosmic horizons create a strange exception. Because different observers experience time differently near horizons, and because the horizon itself represents a boundary where our future light cone ends, the distinction between space and time becomes blurred. From our perspective, a galaxy approaching the horizon appears to slow down, time dilation approaching infinity at the boundary. In principle, if we could somehow retrieve information near the horizon, we'd be seeing that galaxy's far future, events that haven't happened yet from its own reference frame. This doesn't violate causality because we can never actually retrieve that information. The horizon protects chronology by making that information inaccessible. But it suggests that beyond the horizon, time might flow differently, not just at different rates, but in fundamentally different ways. Physicist Julian Barbour has proposed that time is an emergent property, not fundamental to reality. In his view, the universe is a vast configuration space of possible states, and time is just the correlation between consecutive configurations. If this is correct, then beyond the cosmic horizon, where configurations cease to correlate with ours, time as we experience it might simply not exist. We're considering the possibility that crossing the cosmic horizon doesn't just mean entering unreachable space, it means entering regions where the fundamental structure of reality, including time itself, might be radically different.
We've treated dark energy as a cosmological constant, a fixed energy density of space itself. But what if it's something more dynamic? Something that changes, evolves, or operates according to rules we haven't discovered? Recent observations from the Dark Energy Spectroscopic Instrument, DESI, published in 2024, hint that dark energy might not be perfectly constant. The data suggests possible variations in the equation of state parameter W, which describes how dark energy evolves. If dark energy is dynamic, everything changes. A cosmological constant produces a fixed cosmic horizon, but dynamic dark energy could cause the horizon to expand, contract, or behave unpredictably. Galaxies we thought were forever lost might eventually become reachable again, or regions we can currently observe might suddenly cross beyond our causal reach. Researchers at Fermilab are searching for these signatures. They're looking for subtle variations in the expansion rate across different directions of the sky, for anomalies in how dark energy behaves in different regions, for evidence that the cosmos isn't quite as uniform as we thought. If they find it, the implications are staggering. The cosmic horizon might not be a smooth, symmetrical boundary, but a complex surface with structure, variation, and dynamics. Beyond it might lie not uniform space, but a cosmos as varied and complex as anything we observe within our horizon. Here's a question we haven't fully addressed. Why does the cosmic horizon exist at all? The standard answer is that it's a consequence of accelerating expansion. But that just pushes the question back. Why does the universe have accelerating expansion? Why does dark energy exist? Why does it have the specific value it has? If dark energy were just slightly stronger, the cosmic horizon would be much closer. perhaps only millions of light-years away instead of billions. Our observable universe would be drastically smaller. We might never have discovered that we live in an expanding universe at all. If dark energy were slightly weaker, the horizon would be much farther away, perhaps infinitely far away. In that case, the entire universe would remain forever observable and accessible. The fact that we live in a universe with a cosmic horizon at roughly the scale we observe suggests something. Either we're incredibly fortunate, or there's a selection effect at work. The anthropic principle suggests that we observe the universe we do because it's capable of producing observers like us. If the cosmic horizon were drastically different, perhaps intelligent life couldn't evolve. Perhaps the horizon scale is linked to other cosmic parameters necessary for complexity. But some physicists propose a more radical explanation. We created the horizon through observation. In Wheeler's participatory universe model, observation doesn't just reveal reality, it helps create it. The act of measuring the universe, of determining its expansion rate, of observing distant galaxies, might be what establishes the horizon in the first place. This sounds mystical, but it has roots in quantum mechanics. Until measured, a quantum system exists in superposition. Perhaps the universe itself exists in a superposition of different expansion histories, and our observations collapse that superposition into one specific history, the one with the cosmic horizon we observe. If this is correct, then the horizon isn't just a feature of the universe we discover, it's a feature we participate in creating through the act of observation itself. We're approaching the most radical possibility of all. What happens to conscious observers as they approach the cosmic horizon? This isn't just a thought experiment. In the far future, as the horizon contracts, entire civilizations might find themselves approaching this boundary. What would they experience? From an external observer's perspective, our descendants watching from afar, the civilization would appear to slow down, their time would dilate, their signals would become increasingly redshifted. Eventually, they would freeze, appearing locked in an eternal moment just before crossing. But from their own perspective, time would continue normally. They would cross the horizon without noticing anything special. One moment they're in causal contact with the broader universe, the next they're not. No fireworks, no discontinuity, no indication that anything changed. Except they can never send signals back. They're gone, from our perspective at least, forever. This creates a profound asymmetry in experience. We see them frozen at the boundary. They see themselves continuing onward. Both perspectives are valid. Both are true within their respective reference frames. But consciousness complicates this. Conscious experience supposedly requires physical processes, neurons firing, quantum states evolving, information processing. How can a conscious being appear frozen from one perspective while experiencing normal time flow from another? Philosopher David Chalmers and physicist Max Tegmark have explored whether consciousness might be substrate independent, dependent on information patterns rather than specific physical implementations. If consciousness emerges from information processing, regardless of the processing rate, then a civilization appearing frozen to us might still be experiencing subjective time normally. But this suggests something disturbing. There might be multiple valid answers to questions like, is that civilization conscious right now? The answer depends on your reference frame, your definition of simultaneity, your perspective. Consciousness itself might be observer-dependent. Futurist John Smart has proposed the transcension hypothesis,
The idea that sufficiently advanced civilizations might voluntarily move into black holes or other compact space-time structures, trading external space for internal computational density. Could civilizations do something similar with cosmic horizons? If a civilization approached the event horizon deliberately, knowing they'd appear frozen from the external universe's perspective but continue normally from their own, they could potentially exploit relativistic time dilation. From their perspective, they'd cross the horizon and continue existing for trillions of years. But from our perspective, they'd effectively become eternal, frozen in the moment before crossing. This creates a kind of temporal immortality. The civilization would experience their full subjective future while appearing to us frozen in an eternal moment at the boundary. Some physicists speculate that this might explain why we haven't detected advanced civilizations. Perhaps they all eventually approach cosmic horizons or black holes, extracting maximum computational resources from every available joule of energy while appearing frozen or invisible to external observers. The Kardashev scale classifies civilizations by their energy usage: planetary, stellar, galactic. But perhaps there's a fourth level: civilizations that transcend normal space-time by exploiting horizon physics, existing in states we can't observe or comprehend. Seth Lloyd at MIT has calculated the ultimate limits of computation based on the laws of physics: maximum operations per second, maximum bits stored in a given volume, maximum energy efficiency. But horizon physics might allow something stranger: using the boundary itself as a computational substrate. The holographic principle suggests that all information about a volume is encoded on its boundary. If we could manipulate this encoding, essentially programming the quantum structure of the horizon, we might be able to perform computations that are impossible in normal space. This wouldn't be ordinary computation, it would involve manipulating entanglement structures at the horizon, encoding information in subtle correlations, using the universe's fundamental information theoretic properties as a processing substrate. Research teams at Google's Quantum AI Lab and IBM's Quantum Computing Division are exploring whether similar principles might apply to black hole horizons in laboratory analogs. Early experiments with superconducting quantum circuits suggest that horizon-like boundaries in quantum field theories can indeed be used for exotic information processing. If this generalizes to cosmic horizons, it suggests astonishing possibilities. An advanced civilization might construct computations that span the cosmic horizon, using the boundary itself as a quantum computer operating at the theoretical limits of physical efficiency. Such a computation would be invisible to us. We'd see no machinery, no structure, just the horizon itself. But encoded in its quantum geometry might be calculations of incomprehensible complexity. We might be surrounded by civilization's computations.
Every mystery we've explored, quantum mechanics, consciousness, information theory, time dilation, converges at the cosmic horizon. This boundary reveals something essential about reality itself. Reality is not objective, it's perspectival. Two observers can experience genuinely different versions of events, both valid, both true, but mutually incompatible from any single viewpoint. The galaxy crosses the horizon, the galaxy never crosses. The civilization continues, the civilization freezes. These aren't approximations or illusions, they're equally real descriptions of the same physical situation. This is what the horizon teaches us. Reality consists not of absolute facts about the universe, but of networks of relationships, correlations, and causal connections. What's real depends on where you are, how you're moving, what you can interact with.
The cosmic horizon represents the ultimate expression of this principle. It's a boundary not just in space, but in reality itself. Philosopher Carlo Rovelli's relational interpretation of quantum mechanics extends this idea. In his view, properties of systems only exist in relation to other systems. There is no view from nowhere, no objective description independent of observers and reference frames. The cosmic horizon proves this. There is no objective answer to what's beyond the horizon, because beyond itself is relative. Beyond from whose perspective? Accessible to whom? Real in what sense? We're forced to abandon the idea of a single unified reality and accept something more complex, a reality that depends fundamentally on perspective, on context, on the web of causal relationships that define what we can know and interact with. Here's a final paradox that brings everything together. If the universe beyond our horizon continues infinitely, then our observable universe, the region within our horizon, represents 0% of total reality. We have access to literally nothing of what exists. But if the universe is finite, constrained somehow to exist only within horizon-bounded regions, then we have access to a significant fraction, perhaps even all of reality. Our observable universe might be coextensive with the actual universe. Which is true? We cannot know. The horizon prevents us from determining whether the universe is finite or infinite, bounded or unbounded. Both possibilities remain consistent with all observations. But here's what's remarkable. The answer might not matter. If we can never interact with regions beyond the horizon, never receive information from them, never influence or be influenced by them, then do those regions exist in any meaningful sense for us? If existence requires the capacity for interaction, for causal relationship, then perhaps the observable universe is the universe, full stop. This isn't solipsism, the idea that only your own mind exists. It's a recognition that existence itself might be relational, defined by networks of causal connection rather than absolute ontological status. The cosmic horizon forces us to choose. Do we believe in a universe vaster than we can ever access, existing absolutely independent of observation? Or do we accept that reality might be bounded by interaction, that existence and observability might be two faces of the same coin? Neither answer is fully satisfying. Both have profound implications. The horizon ensures we can never definitively resolve the question. We've journeyed from the simple observation that space is expanding to questions about the nature of consciousness, reality, and existence itself. The cosmic horizon has revealed itself to be not just a boundary in space, but a window into the deepest mysteries of physics and philosophy. What does it mean that we live in a universe with edges, that 97% of all galaxies will eventually slip beyond our reach, that the space of possible observation is shrinking, contracting, isolating us in an ever smaller bubble of causality? Perhaps it means that our moment in cosmic history is precious. We exist at a unique time, after the universe has cooled enough for complexity to emerge, but before most of it has crossed beyond the horizon. We can still see the cosmic microwave background, still observe distant galaxies, still piece together cosmic history. In 1 trillion years, none of this will be possible. Future civilizations, if any exist, will live in a universe that appears static, unchanging, eternal. They'll have no evidence of cosmic expansion, no way to infer the Big Bang, no access to the rich history we can still observe. We're fortunate, cosmically, extraordinarily fortunate, to exist in this brief window when the universe reveals its secrets so clearly. But perhaps there's a deeper meaning. Perhaps the horizon exists to teach us something about limits, about perspective, about the boundaries of knowledge itself. Throughout history, humans have encountered limits and transcended them. We thought Earth was flat. We learned it was round. We thought space and time were absolute. We discovered they were relative. We thought determinism ruled. We found quantum uncertainty. The cosmic horizon might be a limit we cannot transcend. Or it might be one we eventually learn to navigate in ways we can't yet imagine, through quantum correlations, holographic encoding, or principles we haven't discovered. But even if we never cross it, the horizon serves a purpose. It reminds us that the universe is larger than our understanding, that mystery remains fundamental to existence, that wonder and humility are appropriate responses to a cosmos that exceeds our grasp. The edge of everything is where knowledge meets mystery, where science meets philosophy, where the known universe encounters the unknowable. And perhaps that's exactly where we're meant to be, standing at the boundary, looking outward, asking questions we may never fully answer, participating in the universe's eternal attempt to understand itself. We've explored the cosmic event horizon from every angle: physical, mathematical, philosophical, existential. We've discovered that this boundary is more than a limitation. It's a revelation about the nature of reality itself. The horizon tells us that the universe has structure we cannot access, that existence might be observer-dependent, that reality consists of relationships rather than absolute facts, that consciousness, time, and causality itself might be more complex than we imagined. We've confronted uncomfortable possibilities, that most of the universe is forever beyond our reach, that we might be living in a simulation with computational boundaries, that future civilizations will be unable to discover what we still can, that existence itself might be finite and relational rather than infinite and absolute. But we've also discovered reasons for wonder. The holographic principle suggests information is never truly lost. Quantum mechanics hints at correlations that transcend horizons. The universe's structure reveals purpose in its apparent limitations. The cosmic horizon exists. It's real, physical, measurable. 20,000 galaxies cross it every day. In a trillion years, 97% of what we can currently see will be gone. This is not speculation. This is the universe we inhabit. But what the horizon ultimately means, whether it represents a final boundary or a gateway to something beyond, remains open. Perhaps it always will. And in that uncertainty lies the essence of the scientific endeavor. We push against limits, we question assumptions, we probe boundaries. Not because we expect to answer every question, but because the asking itself transforms us. The universe has an edge. We've found it, we've studied it, we've contemplated its implications. But the horizon isn't an ending, it's an invitation. To think deeper, to imagine broader, to embrace mystery while pursuing